So it's my pleasure to introduce Pedram Rooshenas. He's been working with us on the DTN program. He's currently a postdoc in Andrew McCallum's lab at UMass. And he's going to talk about deep neural networks for structured prediction. So thank you, Pedram. Welcome.
Thank you for the introduction.
So, sorry, I forgot. So there's going to be a slot for students to meet with Pedram at 2:30 in the 7th floor conference room. So all the students are welcome.
So let's first see some structure prediction problems. Here we have an input image. It doesn't work. That's fine. So we have an input image. The output is a set of labels. So here the structure in the output is that these set of labels that belong to that image are coherent and correlated with each other. Next example is the simplest form of image classification, image segmentation. Here we have binary image segmentation. So the goal here is that to take the input image, here is the image of the horse, and then predict a mask that shows the regions that belong to the horse. Here, the output variables that we have each belongs to the one pixel in the image, and the output variables would show that that pixel belongs to the region of the horse or not. Next example is dependency parsing. In the dependency parsing, we have input text, input sentences from, for example, English, and then the output variables is a sequence of tokens, sequence of variables that each variable showed the index of the head, the root of the parent of that word in the sentence. So here, for example, we know I, the parent of I is son. So the structure here is that this sequence should jointly represent the tree. So this is the structure behind that sequence. Another example is here we have a sequence of noisy image, and each image represents a character. The output sequence here is for each of these noisy characters, we want to represent the exact character. Here the structure is that the represented characters, the output should be a meaningful word in the dictionary. Motion translation is also another example of a structure prediction. In motion translation, we have an input sentence from the source language. Here is from German. And then we have a sequence of output variables that each output, the value of each output variable represents a word in output in a target language. Here is the target language is English. So here, this sequence of output variables should represent a meaningful sentence in English. So we can have many other more complicated examples. Here we want to translate an English sentence, an English query, into the SQL query. Here we have a sequence of the output variable, and each variable represents one element in the SQL. That these variables jointly should represent a syntactically correct SQL. So in all of these problems that we have input, and the goal is to learn a function from input to the output variable. And we want to do this prediction jointly. So we get the input and we have a function that jointly predicts the output variables. So why we care about this joint prediction? Assume the first example about multi-label classification. Here we want to predict the labels that belong to this image. So we can predict comfortably zebra and tree. So it's more likely that zebra and tree appear in the meadow rather than in the ocean. So this configuration is less likely. So we want to use that correlation in our prediction. So this kind of correlation are are everywhere in the structure prediction problems. So let's see how we can traditionally use deep neural networks for these structure prediction problems. So we have the input, we feed it to the neural network, here is COMNET, and then we predict output variable. Here the neural network parameterizes a multinomial distribution for each of these output variables. So for these neural networks to work correctly, these output variables should be independent given the state of the hidden variables in the neural network. Right? This is based on principles in the graphical model. So we want to make sure that these output variables are independent given the neural network that we have. However, for this independence to happen, we need large capacity of the neural network and also many label data. Right? So in practice, that doesn't happen. So what we left is in some dependencies, some interdependencies among these output variables. So we have to capture that dependencies using some structure. So the simplest way to represent that structure is using graphical model. So graphical model in the simplest form is define a factor for each pair of variables. And this factor describes the relation of the state of these variables together. So how likely they are appearing together or not for each state. Right? When we have this information, this correlation of the variable, and then we have this multinomial distribution that we get from the neural network, now we have an inference problem. So this graphical model basically define an energy model over these output variables, and now the goal is to minimize that energy such that these variables come to some agreement based on the correlation that they have and the distribution that they get from neural network. So the one way to find that minimum energy is using message passing algorithms such as Billy propagation. So in a Billy propagation, the variables communicate through the factors to each other such that they can find the states that are in agreement with all of these variables. So in each iteration of the message passing, these variables change their beliefs about themselves based on the correlation that they have with other variables. And then with respect to the distribution that they get from the neural network. So after multiple steps of message passing, they can reach in some agreement, and hopefully that agreement is the correct state that we are looking for. So this message passing is complex, especially because for learning these parameters of the neural network, we have to use this inference inside the learning loop as well. So in practice, people only use simpler graphical model like a chain. So like CRF is basically only one chain of in a graphical model that you can practically compute this message passing, the minimum of this energy. So this chain is incapable of representing complex structure, complex dependencies among the output variables that appearing in the structure prediction problems. So the thing that's happening in the translation, in the SQL example, in image segmentation, they need complex dependencies. So in order to capture those complex dependencies, you need full graphical model rather than chain or low dimensional, like low tree with graphical model, smaller graphical model that you can practically compute this minimum energy. So what we want to do is that we want to replace this thing with neural networks. So neural networks are basically very powerful in correlating output variables, in learning the interactions, right? Instead of only using them for learning the interaction of input variables, we can also use them to learn the interaction of output variables. you can see this neural network on the top as a giant factor that correlate all of these output variables together. Right? Instead of pairwise interaction, suppose that you have a neural network that is a giant factor that interact with all of these variables that we have. So this structure is called the structure prediction energy network, or in short, the SPED. Let's see some other example for this SPED. So for the binary image segmentation, in general, in the feed-forward format, you have 3 channels of image and feed it through the component, then you get the output value. What we do it in a SPED is basically feed the mask, the output variable, jointly with the input as a 4th channel and feed it through the component. Here, in this way, the component sees the correlation of the input variable and output variable jointly, and also sees the correlation of output variable. So here, we get a joint representation of input and output. This is super important for many structure prediction problems. Now let's see the anatomy of a SPED. So you have input X, you have output variable Y, you have a neural network parameterized by W, which gives us at the end some energy function as a function of output variables and input variable parameterized by W. So what we have here, for a given input X, this energy function represents the energy landscape for us. That each point in this landscape is a configuration of the output variables, and this energy function maps this configuration to the scalar value. So this is conditioning on one input. So for each input, we have an energy landscape. Okay. Now the problem is that how we do prediction in such model. Right? In a feed-forward network, prediction is simple. You get the input and predict the output variable at the end. Right? Now we want to find this correct mask. So for the prediction, we have this energy landscape, right? And we assume that the correct output resides in some low energy region in this landscape. So now the problem of prediction is to recover the low energy region in this landscape. So we can start with some random configuration, and then similar to other optimization, gradient-based optimization methods, use gradient of the energy with respect to the output variables to move in the direction of the gradient in this landscape to find low energy regions. So we take multiple steps, and then the final, when we convert somewhere, or we iterate for some predefined iteration, we say that this is our prediction. This makes sense because this energy landscape, this energy function, this energy-based model, what it does, it parameterizes the energy function of a Gibbs distribution. So the configuration that has the lowest energy is the most probable one with respect to that distribution. Okay? Now the problem is that how we train this energy landscape such that the output variables, the correct output variables reside in low energy regions. Then I will talk about learning these algorithms in direct supervision that we don't have a ground truth label. The basic and first algorithm here is based on structural SVM training. So it's margin-based training. So in margin-based training, we have ground truth label. And then we say that for every other output structure in this landscape, we want that the energy of the ground truth be lower than energy of that output structure by some margin. And this margin is defined by the distance between these two variables. Here you can assume that this margin is Hamming loss. Right. So to enforce that for every possible structure output, so it's an intractable problem. You have like exponentially many constraints. So similar to the SVM, what we do here is to find the structure output that violates this margin the most. So in language of the structured SVM, this is called, this inference problem called loss augmented inference. So the goal is to find a structured output that violates that margin the most. Unfortunately, this loss, if you use Hamming loss, for example, this problem is a combinatorial search problem. It's very difficult. However, if we find a surrogate function, surrogate loss for the Hamming loss, for example, if you use cross entropy, you still be able to use similar machinery of the inference in a span, gradient-based inference, because then this is differentiable. You can use the similar gradient-based algorithm to find out a structure.
Sorry, so I think I missed something. Okay, so I get this part that we want the true labels to have low energy, and we want non-true labels to have high energy. Those are the first two terms.
Yeah.
What is the delta doing again?
Delta is basically the margin that you want to enforce.
Oh, I see. That's margin. That's why you call it margin. So the idea is, I see. You want to make this true not just for arbitrary y's that the energy is high, but even y's that are close by, and that's like the analog of a margin in a linear classifier that like things close to the boundary are.
Yep.
Right. So, and then one. Okay. So then the y's. You said it sounded like you wanted the y's to also be structured. At first I thought you were going to say we're going to take the y's to be like other y's from the training data. But it sounds like that's not it, actually.
Now you use only the ground truth label from the training data. That is the part, the structure that we want to like have the lowest energy.
Yeah.
Right. That's come from the training data. These are coming from the sample from the energy landscape. So this basically comes from loss augmented inference. Okay. Then when we find that point, we enforce that objective. So it pulls down the energy of the ground truth, pull up the energy of the output of the loss augmented inference. Okay. So here, using that surrogate function for using gradient-based algorithm to find this to solve this loss augmented inference, like make this algorithm unstable. Because they play with the energy function and the magnitude sometimes because it's cross entropy, and sometimes it's the magnitude is much larger than the energy. They play with each other. So finding the loss augmented inference without that gradient-based inference is a little bit complicated. So we want to like avoid that part. We want to avoid loss augmented inference. So one way is to look at the inference procedure. Okay, and create the computation graph for that inference. So basically what we want to do is unroll the inference prediction. So here, this part is the computation graph of one step of gradient descent. So by unrolling, we create multiple steps of this gradient descent and create a whole computation graph of inference. So what we have at the end is our prediction. So what we want that this prediction be close to the ground truth. So we can optimize this some surrogate loss function again, such as cross entropy, end to end. So we train this graph end to end, and these parts share the parameters with the energy network that we have. So at the end, we have an end-to-end training for the aspects, and it's very stable. The only caveat that we have here, we are still optimizing some surrogate loss. So in practice, you have some other loss for different tasks. For example, for translation, you use BLUE. For multi-label classification, you use F1 score. These are not very consistent with optimizing cross entropy. So what if we want to optimize the task loss directly? So this brings us to value matching, or DVN, deep value networks idea. Deep value network, rather than optimizing task loss, is also have another importance, and that is it has a different interpretation of the energy values. So that is very useful. We can use it in many, many different tasks. It means that we have an energy value, we can interpret it whatever we want. Right? Here, the idea is that it's saying that we have a loss function, and the loss function is also a function of a structure output. And we know that the minimum of that function is 0 at the correct output. Right? So again, we have a function. And also we know that energy function is also function of a structure output. So why not regress the task loss with the energy function? So if you could regress exactly the task loss with the energy function, when we find the minimum energy region, it means that it has the lowest task loss. Right? That is super interesting. So now for regressing that task loss function, what we need is basically many samples to regress it at that point. So how we choose these samples, one is ground truth. Right? We know that the task loss is 0 at the ground truth, so the energy value should also be 0. Then the other point would be the model prediction. Also, we can use alternative heuristic. One is adversarial example. So you start from the lowest energy point and then take a step of the gradient descent. So we know that that point shouldn't exist. There shouldn't be anything with the lower energy than the one that we predict. So we also match that point. And we have a stratified sampling, basically modifying the correct structure output and find some other structural outputs, and then we have a couple of samples from that. So these are all based on the ground truths, except the model prediction. Right? When we have all of these samples, then we can optimize mean square loss here for these samples. Okay? Now, for all of these methods, we rely completely on label data. But we know that acquiring this label data is expensive in general for deep learning models, and it's specifically more complex and more difficult for structure prediction problems, because for each example you have multiple output variables and you have to acquire labels for all of these output variables. So the idea here is that acquiring supervision about the whole structured output is often easier and cheaper than acquiring the supervision for each of them. One way of describing this supervision is through domain knowledge. So what we want from this domain knowledge is to create a reward function that we evaluate each predicted structure output with that function and get a scalar value. That scalar value shows how this predicted output structure is consistent with the domain knowledge that we have. So the reward function basically evaluates each pair of input and output into the scalar reward value. Now, the goal, if we only have this reward function, is to looking the best structure output that maximizes this reward value. So this problem is a combinatorial search problem, and it's not generalizable to all of data if you just search in the reward function, because the reward function is not complete and comprehensive, right? You want to generalize this, and also we want to be able to do gradient descent inference that is super efficient rather than combinatorial search in this reward function that we have. So the goal is to learn a smooth version of this reward function based on the energy-based model that we have, such that it gives us these properties. So the first obvious choice is value matching. But value matching is not perfect if we don't have the ground truth value, if we don't have a correct label of data. Because if you regress a bunch of structured outputs and you don't know the correct one, it's basically just wasting the capacity of the neural network, because there is no guarantees that we can get in this region. As we saw that many of the sampling ideas in the deep value networks as well depends on a ground truth. And there are some other cases. In some other examples of this reward function, we have plateaus in the region of reward function. So for example, the value is 0 for all of invalid structure output that we have. So basically, regressing those reward function with the energy value for this unimportant structured output is based off the capacity of the neural network that we have. So how we can overcome these problems? This brings us to the idea of rank-based training. So in a rank-based training, we say that we don't care about the exact value of the energy function. We don't want to regress the reward values. We don't care about the exact value. What we care about is the optimum point of these two regions. So we only look for an energy function that exactly have the similar optimum point as this reward function. Right? We don't care about the value. So this gives us a super flexibility in learning this energy landscape, because we are not bounded by regressing these values. So we can learn a smooth energy landscape. Now how we can learn it? So in order for these two functions to have similar optimum point, and I should mention that here reward value we're looking for a high reward, in energy we're looking for the low energy, so they are in the opposite direction. So for these two to have a similar optimum point, if we have this constant for every pair of structure output, if the ranking of these 2 points in a reward function is the same as the ranking of these two on an energy function, and if we have this constant for every pair here, then we can make sure that these two have similar optimum point. So basically you select 2 pairs and these two have the same ranking. So if they have the same ranking for every pairs, then all of the features of the energy function and the reward function should be the same. However, collecting like every pair and comparing is not possible. So what we have to do is to sample these pairs. How we sample them is first based on the gradient-based algorithm that we have. So each gradient inference gives us a trajectory. And here we added the normal noise that basically makes this gradient descent sampling algorithm based on Langevin dynamics. It's similar to doing MCMC. So we use this gradient base to collect a trajectory of points. Now we have this trajectory of the inference. We look at every consecutive point, and then make sure that these consecutive points have similar ranking with respect to the reward function and energy function. If there is a violation, then we update. So this algorithm works, but has 2 caveats. First, all the sampling is only with respect to the energy landscape. So what if we trap in some not interesting region of reward function? Or we trap in some local optimum of the energy landscape, right? There is no way to get away from it. And also we have many constraints. For each pair we have 1 constraint to enforce. And this is wasting the capacity of the neural network. We want to look for the most informative pair and then use that for the optimization. So finding the most informative pair is basically only possible if we have some sort of information from the reward function itself. So how we get this information is through search-guided training. So the idea of search-guided training is that we again do this sampling, but we only keep the final point going to the reward landscape and then doing some sort of search initializing at this point. This search is similar to doing some random sampling in the reward function. But we only care about the output of the search that are slightly, with some margin, better than the starting point. This enforces us to always look for something that is a little bit better. So these steps help us to learn the important area of this reward function. We don't have to look for these not interesting area. We only look for the most interesting part. Right? If we cannot find that output in predefined step of the search, we ignore that example, we revisit it again. Hopefully by that point, we have a better chance for the search. So, again, for that point, if we have a violation in the ranking, then we update. Right? Let's see one quick example. We have one variable, 1000 dimension, some handcrafted reward function. And then we learn the energy landscape. Here you can see that it only cares about the important region of the reward function and doesn't care about something that are not interesting. That is very helpful and important part of the search-guided training. We can incorporate that idea into the many of these structure prediction problems. Like in translation, you can use search by finding some more interesting structure output rather than like something that is not informative.
Didn't quite follow. So let me just make sure a few things first. This reward function is not learnable and fixed, right?
Yeah. So it is your domain knowledge, for example.
So previously you said that this reward function is proposed to complement the lack of label data, right? And right now you're saying that this reward function could provide you with additional supervision signals. So what additional information is brought by this reward function?
You will see some example of this in a couple of slides, but you can think of this reward function similar to the reward function in reinforcement learning. Right? You take some trajectories at the end, you fulfill that trajectory, that sequence of action, you get a reward, or you are not getting a reward, right? It's very similar. Here, you have a structure output, you evaluate it based on your domain knowledge into some scalar value, so that's your function. Let's see the example that makes it clear.
Okay.
So we use 3 different tasks to evaluate this method. One is multi-label classification. The reward function here in the multi-label classification is the oracle distance to the ground truth. Then we have citation for the extraction that we use human domain knowledge for that. And also we use some other reward function that is available to us through some non-differentiable pipeline. So for the multi-label classification, we compare these deep value network, this regressing idea, rank-based and search-guided training, and the reward function is distance to the ground truth here. But these algorithms only have idea about the ground truth through this reward function. They never see the ground truth anywhere else. So we see that as we expected, the search-guided training converges much faster, and it also has a better generalization. One important thing that search-guided training have a better generalization is that you recover some partial structures. That is actually an interesting idea to expand for machine translation and these other complex tasks, because we recover some partial structures that are informative for your model. Your model may not be able to predict the whole output in one step. Maybe the ground truth is not reachable, but these partial structures are reachable for the model. And that is important. So we see that search-guided training can generalize much better because we see a couple of these partial structures through the way that are informative. This is an example based on the human domain knowledge. So what we have is a citation text, and the goal is to tag each word with the role of the tag in the citation. So we have, for example, author, date, title, conference, location, venue, this kind of tags, right? And we want to assign one tag to each word, right? So the domain knowledge that we have is basically a Python function that has some knowledge about the problem that we have. For example, we know that if you have a parenthesis, the tag of the parenthesis should be the same as the tag of the words inside the parenthesis. If we have period, the tag of period should be the same as the tag of the word that is prior to before the period. Or we know that if you have a citation text, it's either conference paper, it's either proceeding, journal, or technical paper. It cannot be all of them or multiple of them. Or we know that there's a continuity in these tags. So you cannot have author, title, author, title. There should be a sequence of authors, then sequence of title, sequence of date. So all of this information, we write it down as almost 50 rules in a Python, right? If they are violated, we just penalize the score value. And also we have some other domain knowledge. For example, if the word conference appears in this text, this is always proceeding. It couldn't be part of the title or author name, right? This is the general domain knowledge. Now that we have this scholar function, now we want to learn from it, right? This is deterministic reward function, right? It assigns some value, some scholar value that describe one predicted output, how it's consistent with the domain knowledge that we have. Right? Each of these terms are penalized somewhere. So if you get author, title, it penalized here. Right? So the baseline model here is basically recurrent neural network, and in a recurrent neural network, we have, for each step, we predicted a probability. It's an autoregressive model. We predicted the output value of that step given the hidden state that also depends on the previous outputs. For these kind of problems, the basic way to train task loss is to use reinforcement learning. So here the idea is to maximize the expected reward. And the probability of the output structure for this expectation comes from this output probability that are the output of the recurrent neural network that we have. So the probability factorized over these steps, and then we can use, for example, policy gradient methods to optimize this expected reward function. The energy model that we use for the span is also here. So we have the embedding of the words, we have the probability distribution of each tag, and then combine it together and pass it through the text CNN. So here text CNN jointly sees the input and output representation together. Right? And the filter size also gives it a chance to see multiple output variables. So we pass it through the text CNN, and then at the end we have a MLP and the one scholar value as the energy that we have. So this is just like running beam search, combinatorial inference in the reward function. So it's complex, it's complicated, taking time because we have to do search for every instance separately. And it's not very accurate because it cannot generalize, but this domain knowledge that we have is noisy, right? When you learn an energy function, basically you distill that information from examples into the parameters of the neural network. It's generalized to other examples as well. So because of that, you see that if you run expensive search, you still have a low accuracy. The other base model that we use is policy gradient. So we optimize the expected utility for that. Then we also use max margin idea for the baseline. Here, we're using search to recover the correct output based on reward. And then this last three is based on the energy model that we have. So we see that search-guided training outperforms all of these algorithms, all of these baselines. And the main gradient of this is search-guided, is search. Right? That is very important. I want to emphasize more. The interesting part is that with this rank-based training, we can simply generalize these methods to semi-supervised setting. So in a search-guided training case, if we, in a supervised setting, instead of search, we can use the ground truth. So in the semi-supervised training, whenever we have a ground truth, we use it instead of search. Whenever we don't have it, we use search. This helps us to generalize much better to the unseen data. So here, we see the reward value when we don't use unlabeled data. Here is the reward value when we use unlabeled data in a semi-supervised setting. We see that this gap shows us the unlabeled data helps this model to generalize better to unseen data. That is very important message.
The test data have overlap with the
No, that's not
unlabeled data. Oh, no.
So the last example is shape parser. So in a shape parser example, we have input image. We want to predict the output tree. So this is the program that this program is based on some primitive operation. So the goal is to predict that program that produced the exact input. For example, suppose that you have a logo of a company, you want to predict an output program that if you compile it using some graphic engine, then you get the exact output. Right? So here, for example, one operation is that if you want this ring, you have to subtract this circle from that one. Right? And then to get that shape, you have to add the output with some triangle. So this program gives us that exact logo. Now, if our goal is to predict that program, then we can use that program to compute the reward function. So we can compile it through the graphic engine, we get some input and some output, and we compare the output and input together. This gives us some reward function. Right? Just comparing the output and input. This sort of reward function, these non-differentiable pipelines we have many examples of them in practice. For example, in a SQL parsing. So you can always, if you don't have a ground truth label data for the SQL, you can run it against the database engine, get some output, and use it for computing reward. Right? There are many of these. If you want to predict the code, you can always run the code and use the output for computing reward. So here the baseline is again recurrent neural network. It's encode the image through the CNN and pass it through the recurrent neural network and use reinforcement learning and policy gradient to optimize the expected reward. The shape parser energy model, since we don't have an exact alignment of the image and the output, we have a separate CNN for the image and then pass the output distribution through text CNN again and mix these things, these embeddings, and pass it through the MLP to get energy value. So here, this is very important task here for us because most of these structured output, these parse sheets for the images, are invalid when you predict it. Most of them are invalid programs. So if you pass it through the graphic engine, you just get a black image. So you have a plateau in your reward function that is almost zero. So in this setting, rank-based training and DNNs just fail. They cannot learn anything. And reinforcement learning is also struggling because of this sparse reward that they have. But search-guided training can learn in this environment. So we look at the number of informative constraints, the pairs that violate the region, the margin. Right? We look at these pairs. So at the beginning of the training, we have no violation. It means that we cannot recover any good pair. But quickly we see that the model finds like many constraints. This constraint means that the output is at least valid program. So it means that this energy-based model quickly learned the constraint of the model to predict a correct program, a valid program. So for the future direction, so one thing is that to expand on this learning from domain knowledge. So what I described so far is only using writing down the human domain knowledge as some sort of Python function. So that's difficult to collect human domain knowledge. So it's much easier for expert that we prompt the expert with some query that you want to know the relation of these two output variables. So give me some information about that. Or if we cannot find the better output through the search, we can query the expert to give us some better output structure or make some correction in the predicted output. These are very helpful ideas for expanding the application of search-guided training and learning from human domain knowledge. Also, we can combine variety of sources together. So I'm quickly going forward. So the main point here is that I want to sell this idea as a general purpose toolkit to learn from indirect supervision. So whenever some practitioner want to use this neural network for their task, they can write down the domain knowledge in some way with this interaction in a human, in the loop interaction that we have, and then they basically make it working, right? Instead of going and collecting label data. This is like, I've seen like many researchers that in other fields that have this struggle, especially out of the main field of computer science. So we can also use this rank-based training with like a general way of solving a structured prediction problem. For image captioning, we have this CIDR task loss that again is inconsistent with the cross entropy. So people using expected reward function, maximizing expected reward function to reinforcement learning algorithm for this kind of task. But here, without having the energy function in SPAN, we can only like decompose the energy function over this autoregressive format that we have and simply use rank-based training. We saw that based on the preliminary result that we have, the rank-based training converges much faster rather than reinforced algorithm. Also, I want to mention that this energy-based model are everywhere in the practice. You can create them from other things that you have. For example, this is the BERT model that is used for training the language models. So it takes an input and mask some parts of the input and try to predict the mask word. And this is a graph of transformers, a complicated model. So what we can do is to replace the head of this BERT and map it to some scalar value. Now, if we have some sample or some neural machine translation, and then this creates for us some sample output, then we can use this sample output using the same idea in the rank-based training to train this W. And just like with this simple case, we saw that it improves the performance of neural machine translation. So I want to establish this idea of the rank-based training and search-guided training as a general framework for direct loss minimization. So the final point is that energy-based models in general are very powerful, and they are a way to representing probability distribution. But computing the partition function, the normalization constant, is difficult, intractable in general for having these generative models. But using this Langevin dynamics or some other ideas, we can just approximate it with the samples or doing some sort of training the vector field. There are many ideas right now. And then we have generative modeling. There is a huge interest in the community for using this generative modeling. For example, for image modeling, they show that they are on par with GANs, right? These giant energy-based models, right? And then you can do sampling. They are stable. They don't have a mode collapse problems. They're interesting way to represent different images. You can use it for model-based reinforcement learning to model the environment, and then you can sample from that environment, or you can use it for memory models. All of these are very recent works. Or very recently, they use it to combine the generative modeling, discriminative modeling to like make the classification more robust and stable, and for especially for out-of-domain distribution. So one thing that is missing is modeling high-dimensional structured data such as text. So these image cases are pretty simple because they are sort of continuous problems. They are not structured. So for a structured problem like a text, these gradient-based approaches are a problem because we have to traverse high-dimensional out to the space. So in an example of translation, each variable text, the dimension of each variable is the size of the dictionary of words that you have. So this gives us very huge space, and traversing this huge space using gradient-based algorithm is super difficult. So what we have to use hidden variable to reduce the volume of this space, right? So one idea is that to define this energy-based model over that hidden latent space. So this latent space is much smaller and easier to work with, and we can use gradient descent in this latent space, and then use some feed-forward network to map it to the output space, right? These ideas are interesting for modeling text in this domain using energy-based model that I want to work on that. So I can skip this thing, and I want to also acknowledge my collaborator at UMass that helped me to come up with these ideas and each in some way. Thank you.
Okay. We have time for a few questions.
In your slides, do you have examples showing how randomly sample, initial prediction evolved towards the final prediction by the gradient descent method? Your inference is taken by gradient descent, right?
Yes.
So do you have examples showing the process that is?
That was like the very beginning of slides. Actually, I use these examples. These are going from like the initial point to predict output. I took them from the actual model.
Do you have the ones for the discrete structure?
I don't have it on my slides for the discrete structure, but for one thing is that for discrete step, one thing that I hide it in the slide for the sake of simplicity is that after each step, you have to project back to the simplex of the structure output. So we have a projected gradient descent rather than just like gradient. But after each step, we project it back to the feasible output space. So it's basically a simplex, for example, in case of translation over all of the dictionary that you have.
So I was curious about the rank-based constraints. So you said we're going to incorporate rewards by saying that the difference in energies between two states should be the same sign, I guess, as the difference in rewards. I assumed that you're updating your parameters W with stochastic gradient descent somehow. Yeah. So is it right to think that the way that you impose these constraints is that you add to your loss function the constraint about matching the direction and then you take a gradient with respect to that as well. Maybe I could say it in a simpler way. Is that just a regularizer that you add to the loss function? About the pairwise reward ranking constraints?
So we, in the objective that we have is exactly similar to this objective.
Yeah.
So this is the thing that we optimize plus some regularization of the weight.
Right.
So
yeah, and then when you add these constraints, one more term in that
objective. So this is the constraints.
Yeah.
These are the points that violating the output. So we get these samples from the output. We find the pair that we want to optimize. So the pair basically would be YL and ground truths, and you optimize it for that over the whole batch.
Okay. So how does the reward come in that case? I mean, you were already doing
in the rank-based training, reward is the difference between the reward of the one point minus the reward of the other.
Okay.
The margin is defined by the difference in the reward.
I see.
Okay, so I think one of the hypotheses that came in the first slides was that introducing neural networks and probably increasing complexity across these 1 to 5 algorithms kind of helps us. And intuitively I can see that, but do you have actually so have you somehow investigated? Have you done error analysis basically to figure out what kind of things are your models actually compared to baselines? And also, I see that most of the scores are somewhere I think around, presumably. But what is in the rest? 40, 50 doesn't get right.
That's the gap between supervised training and indirect supervision. If you go to the unsupervised training, the gap is like much larger. So still there is a huge gap, and that we have to cover that gap. Right? That is how we represent the human knowledge, how we use different sources to reduce that gap. Right? So fully supervised training, if you have labeled data, is the ultimate solution. Right? If you have enough labeled data, so use it. But the thing is that we don't have it in many cases. It's very difficult to accurate. Right? So we are going in that direction to what we do when we don't have the labeled data, or we don't have enough labeled data in a semi-supervised setting.
Right. So thanks for clarifying. In that case, again, what are the things that your model doesn't get right? Can you find a way to somehow characterize the?
That's basically the lack of information that we have, the lack of supervision. So the human domain knowledge that we have is just basically 50 rules. It's not like comprehensive, right? It doesn't cover every possible information that you get from labeled data, right? It's basically a set of constraints and a small set of domain knowledge, right? The only thing that you get it is if you mix it with supervision, with the labeled data, you get this improvement over supervised setting. Let's say that. So here is only supervised training, and in other cases we also use supervised training, like with the DNN supervised training. And then this domain knowledge, if we use it in addition to the labeled data, it helps us to improve the performance, right? But if you remove all of the labeled data, then the gap in the supervision is the problem.
So there are two types of structure you're incorporating. One is the structure in the value function, which is sort of something that's coming as a reward potentially from structured constraints, and the other is the actual structure within the output variables and structured prediction. it seems like one would cannibalize the other, right? So isn't what you're doing in the structure prediction space sort of akin to what you have as these sort of like labeling functions or kind of heuristics that give you the reward space? So how do you actually draw the distinction between them? Is this the structured prediction learning basically what the human put as a reward function, or is there a deeper story there?
So the whole idea is that when we have a representation, when we have this capacity in our energy-based model, they should be able to learn those implicit structures from data, right? So if you don't have a labeled data, you encode these structures in the reward function as a constraint. So again, those are information we incorporated in the constraints in the reward function, and you can learn from that and transfer this knowledge to the energy-based model. So and what spends an energy-based model only provide is a rich representation, right? It's the way you have enough parameter to correlate these structures, these output variables.
Yeah, but you see kind of what I'm saying, right? Like, so you could say, okay, what we've gotten in the spend is exactly what the human told us in the reward function, and that's good, right? Like, I'm not saying that that's a bad outcome to say we had some heuristics, and then you were able to kind of represent those heuristics as a structured, set of constraints in the variable space. But ideally, what you want is to learn those things, right? To do the structural learning yourself. And it's not clear to me whether, as part of what you're doing, you're generalizing to structures that aren't in the heuristics that that are in the reward space. So I think that's sort of the crucial thing that you want from this sort of model, right? Is not just to parrot back what the human told you.
So one thing that a spend can do is basically the reward function that you have is like information for each specific task, right? Each specific example, right? And then what the spend is doing is generalize all of these information about different examples and learn something from it.
Right, and so do you have examples of that? I think this goes to Philip's question. Can you show something that's like a generalization of a bunch of heuristics, which is novel in some way beyond what a human told you, and then that might lead to some errors or might lead to some wins?
So this is the what you learn from the only reward function, right? And then you generalize it through the spend. That's only like this is the only source of supervision that you have, right? And using combinatorial search, this is the output that you get from combinatorial search. What this performance gap shows you is how a spend generalized over this reward function, right?
Right, but right, like you could show what that structure is, right? Because you know what the weights are between the dependencies. Then you could say this is what the new rule would look like, the kind of generalization.
I don't have that information to show you that exactly this is the rule of generalization. I'm not sure that's exactly taken from that.
Okay. I think if people have questions, there will be opportunity to meet with Pedram later in the afternoon. So let's thank him for the talk.